Hi everyone, so the topic for this video is everything about Mosfet. In this video, I will explain about the introductions of the Mosfet, type of Mosfet, working principles, characteristics, applications of Mosfet, and also the comparison between Mosfet, BJT and FET. Mosfet or metal oxide semiconductor field effect transistor is a unipolar transistor and usually used in voltage control devices. Mosfet consists of 3 or 4 terminals, which is gate, drain, source and body. Gate as a controlling terminals is made out of the metals and insulator oxide sit between the gate and channel. It is used to prevent current from flow out and in of the gate. So here is the diagram for Mosfet and the symbols for N-channel Mosfet and P-channel Mosfet. Mosfet consists of source terminal, gate terminal, drain and body terminals. The metals and oxide layer is connected between the gate and the body. Inside the body have two regions, which is channel region and also the substrate region. For the N-channel Mosfet, the direction is to the inward, while the P-channel Mosfet, the direction is to the outward. This is the difference between the symbols of N-channels and P-channel Mosfet. So, this is the symbol for depletion N-channel Mosfet. The D, S and G terminal are separated from each other, and the directions is inward for the N-type channel. So here is the N-channel types of depletion Mosfet. In this type, the channels is made out of the N-type material and the substrate is made up of the P-type material. The drain terminals and source terminals are connected to the N channels. The gate terminals not directly connected to the N channel. The gate terminals isolated from the terminals by silicon oxide layer. They have metallic contact from the drain, source and gate terminals. And the insulating layer of the N channels is made up of the semiconductor materials. There is no current will flow in the gate terminal as the input impedance of this gate terminal is very high. It is suitable to applications in the minimum power consumptions. The gate and the source terminals are connected together to the ground. So, we can assume that the initial VGS is equal to 0. The voltage applied between drain and source terminals and at it causes the electron in the N channel attracted to the terminals. Electrons start to moving from the source terminal to the drain terminals. The current established in the N channel. When we increase the voltage applied, the current flow in this channel also will increase. This process will continue until all the electrons contribute in the flow of current. After all the electrons contribute in the flow of current, they will remain constant even when we increase the voltage applied. The conventional current will flow from the D to S. When we apply the negative voltage of the VGS, the negative voltage at the gate will push the electron to the substrate, and the hole in the P types will get attracted towards the electron. The electron will combine with the holes and the recombination rate will increase if the applied negative voltage increase. Hence, it will reduce the number of the free electron in the N channels. It also will reduce the flow of the current.
So when we apply positive voltage at the gate terminals, the electron which are the minority carrier in the P substrate will attract to the N channels. So the free electron in N channel will increase and also the flow of the current in the N channel also will increase.
For depletion MOSFET, this is the symbol for the P-type depletion MOSFET. The drain gate and the source terminals is separated from each other as it is depletion MOSFET, and the direction is to the outward as it is the P-type channel. So here, the diagram for the P-type channel depletion MOSFET. In this type, the channels is made out of the P-type semiconductor materials, and the substrate is made out of the N-type materials. For this type, the polarity will be reversed. The VGS will be positive and the VDS will be negative. The holes in the P channel get attracted to the negative terminals and establish the flow of hole. The conventional current will flow in the same direction. When we apply the positive VGS, the hole push toward the N-type substrate, and the electron at the N-type will attracted to the P-type channels. So the hole and the electron will recombine as we increase the VGS, and the number of the holes in the P channels will decrease, hence it will reduce the current flow. So now this is the N channels for the enhancing MOSFET. This is the symbols for the N-types enhancing MOSFET. We can see that the drain, gate and the source terminals is connected to each other, and the directions is towards to the inward for the N-type. So this is the diagram for the N-type channel enhancement MOSFET. It's similar to the depletion type MOSFET. The channels is made up by the N-type materials, and the substrate is by the P-type materials. The drains and the source terminals is connected by the metallic contact with the N channels. The outside layer isolates the gate terminals and the P-type substrate, but there is no channels between the drains and the source terminals. In this type, the applications of the control voltage enhance the number of the charge carrier in these regions, and due to that, the channels is getting created. When the VGS is equal to 0, the voltage between the drains and the source terminals is applied due to the absence of the channels. So, the channels will remain off as it is no current flow. So, when the voltage VGS is positive, the substrates and the source terminals will connected together to the ground, while the positive voltage is applied between the gate and the source terminal. Okay, so we assume that the VGS is equal to 0. So the holes is the majority carrier in the P-types and the electron is the minority carrier. When the positive voltage is applied at the gate terminals, the hole will push from the gate, and the electrons in the P-types will attract to the gate. When we increase the VGS, there is more hole push to the substrate, and the electron will recombine and move together to the gate terminals. But then they cannot cross as it consists of insulating layer, and they start to accumulate. So they have electron layer created near to the outside layer, and it will act as the channels between the drains and the source terminals. Then when we apply the voltage between the drains and the source, the currents will flow through the channel. So now we can find the threshold voltage by the voltage when the inversion layer occur. When the VGS is higher than the threshold voltage, they will have current flow and increase the width of the channels. But along with these channels, there will also be a depletion layer around these channels, because if we observe, there are two PN junctions which are reverse bias. So the first PN junction is formed between this drain and the substrate, and the second PN junction is formed between the substrate and the source terminals. And both of these terminals is in a reverse bias. So now we can assume that the voltage is larger than the threshold voltage. When we apply the VDS, the electron will get attracted to the positive terminals. The conventional current will flow from the drain to the source terminals. The width of the channel will reduce at the drain terminal sides due to the positive voltage at the drain terminals. The PN junctions be more reverse biased. That's why the depletion regions increase and reduce the width of drain terminals. So when we apply the voltage from the drain to the source terminals, the voltage difference will reduce. So when the VD increase, the voltage difference will be reduced. So the gate terminals, which is toward the drain side, will be less positive than the other side.
This region will attract less electron compared to the other side as the width is narrower. If the VDS keep increasing, it will reach the pinch-off conditions and saturate the flowing of drain current. It known as saturated voltage and can express as VGS minus threshold voltage. The pinch-off occurs when the difference voltage of the gate and drain terminals is equal to the threshold voltage. The channels getting created between the drain source terminals and the threshold voltage. When we increase the VDS and fix the VGS, the voltage difference will reduce, then the threshold voltage and the channels form towards the drain terminals. It makes the current through the channel become zero. Current will flow through these channels and this ID will get saturated because of the electron still can pass through and the channel can cross the depletion layer due to the electric force. So the second types of the enhancement MOSFET is P-type channels. In this type, as you can see, the drain, gate and the source terminal is connected to each other and the directions is toward the outward as it is the P-type channels. The difference between the P types and the N types is the symbols for the directions. So now we move to the P types channels enhancement MOSFET. In this figure, we can see that the N type materials is used as a substrate and the P type material used as the channels. The P types channels connected to the drains and the source terminal through the metallic contact. In this P channels MOSFET, the polarity is reversed. The channel will be formed whenever the applied voltage VGS is negative. And mathematically, we can say that the channels will be formed whenever this voltage VGS is greater than the VT. But here, all the voltage will be negative. The current start to flow through the channels when the VDS is applied between the drains and the source terminals. For the P channels MOSFET, the pinch-off conditions will occur whenever this voltage VDS equal to VGS minus VT. But here, all the voltage will be negative. So generally, MOSFET can exhibit in three operating regions. The first one is cut-off region. Cut-off region is a region in which the MOSFET will be off as there will be no current flow through it. In this region, MOSFET behave like an open switch and is thus used when they are required to function as electronic switches. Second is ohmic or linear region. Ohmic or linear region is a region where in the current IDS increase with the increase of the value of VDS. When MOSFET are made to operate in this region, they can be used as amplifier. The last one is the saturation region. In saturation region, the MOSFET have their IDS constant in spite of an increase in VDS and occur once VDS exceeds the value of the pinch-off voltage. Under these conditions, the device will act like a closed switch through which a saturated volume of IDS flow. As a result, this operating region is chosen whenever MOSFET are required to perform switching operation. So this figure is referred to the N-channel division type MOSFET. The transfer characteristic of N-channel divisions MOSFET shown by this figure indicate that the device has a current flowing to it even when the VGS equal to 0. This indicates that this device conducts even when the gate terminals is left unbiased, which is further emphasized by the VGS0 curve in the figure. Under this condition, the current through the MOSFET is seen to increase with an increase in the value of VDS until VDS becomes equal to the pinch-off voltage. At this, IDS will get saturated to a particular level IDD, which is saturation region of operations, which increase with an increase in VGS. Further, the locus of the pinch-off voltage also shows that VP increase with an increase in the VGS. However, it is to be noted that if one needs to operate this device in cut-off state, then it is required to make VGS negative, and once it becomes equal to negative VT, the conduction through the device stops as it gets deprived of its N-type channels.
So now this is the diagram for the P-type channel depletion MOSFET. This figure shows that this device will be normally on and thus conduct even in the absence of the VGS. This is because they are characterized by the presence of a channel in their default state, due to which they have non-zero IDS for VGS equal to 0 voltage. Although the value of such a current increase with an increase in VDS initially, which is the ohmic region of operation, it is seen to saturate once the VDS exceeds the VP. The value of this saturation current determined by the VGS, and it seems to increase in negative directions as VGS become more and more negative. For example, the saturation current for the VGS3 is greater than for VGS2, which is however greater when compared to that for VGS1. This is because the VGS2 is more negative when compared to VGS1, and VGS3 is more negative when compared to either of them. Next, one can also note from the locus of the pinch-off that even VP start to become more and more negative as negativity associated with the VGS increase. Lastly, in order to switch this device off, one needs to increase the VGS such that it becomes equal or greater than the threshold voltage. This is because when done so, the device will be deprived of this P-type channel, which further derive the MOSFET into their cut-off region of operation. So now this is for the N-type channel for enhancement MOSFET. This figure shows the transfer characteristic drain to source current IDS versus gate to source voltage VGS of the N-channels enhancement MOSFET. From this, it is evident that the current to the device will be zero until the VGS exceeds the value of the threshold voltage. This is because under this state, the device will be void of channel, which will be connecting to the drain and the source terminals. Under these conditions, even an increase in VDS will result in no current flow, as indicated by the corresponding output characteristic, as shown in the figure. As a result, this state represents nothing but the cut-off region of MOSFET operations. Next, when VGS cross VT, the current to the device increase with an increase in IDS initially, and then saturate the value as determined by the VGS. As the VGS increase, the saturation current flowing through the device also increase. As we can see in the figure 1b, the IDSS2 is greater than the IDSS1, as the VGS2 is greater than VGS1. The IDSS3 is greater than IDSS2, as the VGS3 is greater than VGS2. Further, this figure also shows that the locus of the pinch of voltage from the VP is seen to increase with the increase in the VGS. So, this is the figure of the characteristic for P-type enhancement MOSFET. In this figure, it shows the evidence that the IDS remains zero, which is at cut-off state, until the VGS become equal to negative VT. This is because only then the channels will be formed to connect the drain terminals of the device with its source terminals. After this, the IDS is seen to increase in reverse directions, with the decrease in the value of VDS. This means that the device is functioning in the ohmic region, wherein the current through the device increases with an increase in applied voltage. However, as VDS becomes equal to negative VP, the device enters into saturation, during which a saturated amount of current IDS will flow through the device, as decided by the value of the VGS. Further, it is also to be noted that the value of saturation current flowing through the device is seen to increase as the VGS become more and more negative. For example, the saturation current for the VGS3 is greater than the VGS2, and the VGS4 is much greater than both of them, as the VGS3 is more negative than the VGS2, while the VGS4 is more negative compared to either of them. In addition, from the locus of the pinch of voltage, it is also clear that as the VGS becomes more and more negative, even the negativity of the VP also increases.